Okay, nice. Okay, guys, thanks for coming. So today we're going to review what we learned last week. So it's about fairness and all the stuffs. Okay, so question one resembles the question one in the homework. I think there was question two. I think so. Yes, I was skipping one of the questions in the homework. I think it was I was skipping inequity aversion. So that part, I think, it's not that difficult to solve. So let me skip that question. And then I also found that this fairness equilibrium of Rabin, 1993 or 4. So I thought this was also, so this was also complicated for me. So I think it would be nice if I can review this concept with you guys. Okay. So yeah, so as the professor told us, it's one of the most difficult concepts that we learned in the class, possibly in whole economics class in our undergraduate studies. So I think it might be useful to go over this question. So the numbers are changed. So the specific numbers in this question are different from the actual homework. Okay. Okay. Then let me start from the first question. Suppose the dictator's utility looks like this. So what I changed in the homework is that I changed the style of the utility function. Okay. So in the homework, if you put sigma equal to 0.5, then it becomes almost identical to the homework question. The answer actually will be exactly the same. Okay. So you can think this is a bit more general case than the homework. And then this function, does anyone know the name of this function? It has a name. It's a very famous function in economics. This is called CRRA. So this kind of function exhibits CRRA. We just sometimes call it as a CRRA function. So the exact meaning is constant relative risk aversion. So there's something called relative risk aversion parameter. If we compute that number, if we compute relative risk aversion, it will be constant for this type of functions. So not very important for this class, but I thought it might be useful if we try to implement or use this function for this question. So yeah, so let's see what happens. Any questions before I move on? Okay. So the setting here is that so I think everyone would be familiar with what is going on, but let me just try to remind you what is going on in this question. So dictator has $10, okay, and then he's keeping X amount of dollars and give 10 minus X amount of dollars to responder. Okay, so yeah, so basically this is what is going on, and then here's some type of other regarding preferences. So he's thinking about the utility of the opponent. Okay, so this is a dictator where he also thinks about this m minus x 1 minus sigma for the opponent. So he's not just maximizing his own consumption utility. He's also trying to so he also has in mind what the other people will get by his action. Okay, so solving this problem is not difficult. It's very simple. Step one. So if I go into the solution of this problem, step one will be differentiate with respect to this WRT means with respect to x. So x is what he controls. So we differentiate with this and set to 0. I forgot to say that differentiate this our utility function and then set to 0. So the marginal benefit and marginal cost will be the same. So if you do that, maybe I can use a different color here. Then du dx will be, let me go step by step. Differentiate this function with respect to x plus alpha. Differentiate m minus x, 1 minus sigma, 1 minus sigma. Differentiate with respect to x. Okay. So for those of you who are wondering what I'm doing here, I was just putting these functions into here, and then I was just putting this differentiation sign. So that's all I did. Okay, so nothing technical here. Any questions so far? Now, one nice thing when we use CRRA function is that if I differentiate this first blue box, then I will have, I had 1 over 1 minus sigma first. And then if I take this guy, exponent, if I take exponent to the ground, then I will have 1 minus sigma here. Then I will have x 1 minus sigma minus 1. Okay. Just to be clear, let me highlight the parts that is affected by the differentiation. So 1 minus sigma is resulting from this differentiation. So take 1 minus 1 here. Plus alpha. And then we do it in the same way. 1 over 1 minus sigma was already there. Okay. Times. I'm taking this 1 minus sigma to the ground. So this guy. Okay. So this guy came to the ground like this. Then I had m minus x, and then 1 minus sigma. And then if I differentiate, I need to take minus 1 from the power. Any questions? Then let me proceed. Copy, paste. Color green. You can see that these guys get cancelled out. 1 minus sigma is also cancelled out. This 1 in the power is also gets cancelled out. So 1 minus 1 is 0. So what is left is just x minus sigma plus alpha m minus x minus sigma. Okay. Any questions? Don't forget to set it to 0. Okay, so this is important. Okay, so we need to set the resulting equation to 0. Okay, so this is the key part. I made a mistake. Do you know where I made a mistake? Let me give you a hint. Mistake is here. The sign of this is wrong. It should be negative. Minus this term, minus this term. Because here we have m minus x. So minus term should be popped out like this. So I'm sorry for this mistake. So this one also has to be negative. Okay. Yeah, so we are almost done. If I recommend you step 2, then I would put m equals to 10, alpha equals to, what was it? 0.9. This is a typo. So so I thought that this should be 0.09. Yeah. Oh, I'm sorry for the typo. So when I designed this question, it was meant to be 0.09. So you will see why it has to be 0.09 soon. I mean, 0.9 also makes sense. You can compute the answer, but if it is 0.09, then it gets a little bit easier to solve. So you'll see soon. And then sigma was -2, just 2. Okay. So substitute the values on the left. Then we have x minus 2 minus 0.09, 10 minus x power to 2 equals to 0. It's the same as copy, paste. If I take the right-hand side, if I take the second term to the right-hand side, then I will have this equality here. Okay. And then we have x squared minus 2 . Let me take 0.09 to the left. It's not difficult. Like this. So I'm dividing each side by 0.09. Then I will only have 10 minus x power to -2 left. So the next step, let me power each side by -1/2, which gives x minus 2, 0.09 power to this, 10 minus x 2, like this. Of course, you guys can be much more faster than me. I'm just trying to go really step by step. Okay, so here we have x, and then we have 0.09 square root equals to 10 minus x. So here, we can see why I put 0.09 here. If I take a square root of 0.09, then it's 0.3. Yeah, so that was the only reason why I used that number. So in the exams, I think the professor will try to put very nice numbers that would require minimal use of the calculators. So that's my guess. So if something is too messy, then you should, I think you might want to take a step back and check if there's no mistake. Anyway, so yeah, we're done. So now if I just rearrange this term, I will have x equals to 10 over 1 plus 0.3, which is 7.692. Okay. Oh, just as a reminder, so some of you may have noticed that I already uploaded something like an answer key for this discussion. So this time I tried to type the answers because the next question can be a bit messy. So if I upload my handwritten answers, then it can be very, very complicated to understand. So this time you will see my typed answers on Canvas. It is already uploaded on Canvas. So you can also look at that one too. if my handwriting is illegible. Anyway, any questions about question 1? So this is the end. So the dictator will keep $7.692 and then give the rest to the responder. If there's no other questions, then let me move on. So question is 2 parts. What is the Nash equilibrium of this game? Show that CC, so these 2 actions, these 2 strategies, is also a fairness equilibrium of this game. So it's 2 parts. First part is a bit obvious to solve, showing what is the Nash equilibrium of this game. So let me do this here. How do we find Nash equilibrium? We find best responses and then pick the outcome, or pick the strategy profile where the best responses cross. If this sounds too abstract, let me show you how we do that. So if I'm a row player, so let me call row player as P1 and column player as P2. And then we can pick his best responses to P2's actions. So suppose that P2 have chosen D, then I'm choosing between 10 and 5. Obviously 10 gives the higher payoff. So my best response should be this one. So let me tick here. If the column player chooses C, then what is my best response? It is also choosing D because 25 is larger than 20. Any questions so far? And then if the row player or P1 chooses D, then I'm choosing between 10 and 5. 10 is larger, so I will choose this. P2 chooses D. If row player chooses C, he will choose D. So here in red box, we have, so this is the only cell where best responses cross or coincide. Okay, so DD. Let me check. If row player chooses D, he chooses D. Row player chooses C, he chooses D. Okay. Oh, okay. So it seems that DD is a Nash equilibrium. When I designed this question, actually I made CC to be a fairness equilibrium. So you will also see this soon. Okay. So Nash equilibrium was DD in this case. Okay. So let me move on. So let's see how we compute fairness equilibrium, how we show that. Okay, so suppose that P1 thinks that P2 plays C. So this is my first order belief. So in the lecture note, we call this as B2, which equals to C. And then P1 thinks that P2 thinks that P1 plays C. Okay? So I need to think about what my opponent is thinking about what I'm going to play. Okay, so I'm guessing that so P2 will think that I will play C. So this is my second order belief. I think we call it as C1. And this also equals to C. And how fair does P1 judge P2 to be? So let's try to solve this question. So what is pi 1h? So suppose that, fix the column here. Okay. So we are thinking about how fair P2 is. Oh, I'm sorry. So we need to fix here. So suppose that I've chosen C, okay, and then P2 has two options, D and C. And based on what he chooses, I'm gonna evaluate how fair he is, okay? So in this case, we fix this red box, okay? And then evaluate how fair P2 is. And then we need to focus on what we get, what the player one get. So we are comparing between 5 and 20. So pi 1h is the best. So it's the maximum payoff that the P1 can get, which is 20. Okay. Any questions? Pi 1 min is just the minimum payoff that I can get. So it is 5. And then pi 1 e is the equitable payoff. We just need only one input for this function. So for this one, pi 1h is 20. What is pi 1l? It's the minimum payoff among Pareto efficient outcomes. Okay. So it's 525 PE. PE means Pareto efficient. So we are just comparing 525 versus 2020. So if I can make all persons utility increase, then at that point, it is not Pareto efficient. Okay. But if I see here, if I increase the utility of this person, player one, so if I make 5 to 20, then there's something that I need to sacrifice. 25 should decrease to 20. So if I make one person better off, then the other person should be worse off. So in this case, these two guys are all Pareto efficient allocations or outcomes. And then, yeah, so among all the Pareto efficient allocations, the minimum payoff player one is 5. So let me put 5 here. So this is 25 over 2. Any questions? And then this pi 1 CC is the payoff when player one plays C, player two plays C, and payoff of player one. So suppose that they all play C and C, which is this blue circle here, then player one's payoff is 20. Okay. So which means that I have 20 minus 25 over 2. Pi 1h is 20. Minimum payoff was 5 based on step 2. Now, let me write here. This was step 2. This is just read from the table. This is coming from step 3. This is coming from step 1. And then if I compute the values here, then I will have 240 minus 25. 20 minus 5 is 15. This is 15 over 2, 15. So we have 1 over 2. Okay. Let me check if I didn't make any mistakes. Okay. So I changed the question, and then so I only changed the question in my laptop, and then what I see here is different. Okay, fine. Yeah, we can just try to solve this question. So I will also upload this annotated notes. Okay, that's cool. And then I will also so I have another question with a bit different numbers. Answer key for that one is already uploaded on Canvas. So you have two practice questions, two additional practice questions for this concept. Okay. Okay. I'm sorry for making small mistakes here. Yeah. So the numbers in here. So I was making a different versions. And then this is one of the old old versions that I made, but it's fine. It's fine. We can use any numbers for our practice. Okay, guys. Let me move on. How fair is P1 towards P2 if she plays C? Okay, so at the top, I mean, for question question one, we were thinking about F2 ball. So how fair P2 guy is. Now we are thinking about F1. Okay, so how fair I am. Okay, so to evaluate this, we need to think about the second order belief and then player two's actions, which means there's a typo. This should be B2. This should be B2. Yeah. So we need one action from my opponent B2. We need second order belief of my opponent, which is C1. Sorry for making many typos. So this is a very complicated concept, which means that there are many rooms for mistakes or making typos. Yeah. But the fundamental way of solving the question doesn't change. Okay, so we now fix player two's actions. Okay. So now I'm sorry. We now fix player one's actions. I'm sorry. Yes, yes. So I'm sorry. So we are fixing player two's actions, which is C. And then based on what I choose, player two will think about how fair I am. Okay, so let's move on. I think this was not a typo. Yeah, that's fine. Okay. Let me copy and paste this one. Paste image here. So we have a small box here to see what is going on. So what is pi 2h? So it's the maximum payoff for the player two. And in this case, it is 20. What is pi 2 min? So pi 2 min is this one, 5, okay, which is the minimum payoff for player two. And then what is pi 2 e? Also, there's typo here. One argument is fine. So pi 2h coming from step 1, it is 20. And then we need to see if all of these are Pareto efficient or not. They are all Pareto efficient because if I decrease this, yes. So if I increase 5 to 20, then 25 should be decreased to 20. So if I make player two better off, then player one will be worse off. So all of them are Pareto efficient. Okay. And then among Pareto efficient allocations, the minimum payoff is 5. So pi to L is 5. And we take the average value, which gives 25/2. Yeah, so I just noted that this was the typo. C1 should be B2. Okay. Okay. Yeah. So yeah, based on step 1 to 4, let's calculate this. Then this is so pi 1 CC. So this is the payoff when both player 1 and 2 chooses C. So in this case, the payoff is 20. I think this should be pi 2. Pi 2 for here, pi 2 for here, pi 2 for here, pi 2 for here and here and here. Okay, yeah, so I will also fix this typo. Sorry for many typos here. Okay, so if I move on, so we are just using the values that we computed above. We have 25/2. And then we have 20. And the minimum payoff is 5. And here we have if player 1 chooses D and player 1 chooses C, then the payoff becomes different. It is so if player 1 chooses D, if player 2 chooses C, then the payoff is 25. So we have 25 in here. 5 minus 2, 20 minus 5. So this one, we have negative 5. We have 15/2 divided by 15, which is 1/2. So the first one is done. And for this one is 25/2, 15, which is 5/2 divided by 3, which is 5 divided by 6. Okay. And then you see that there's a way to speed up this process because the terms here are the same as terms here. These 3 guys are the same. So once you evaluate pi to h, pi to mean, pi to e, then you're just varying the payoffs, and then you can just recycle what you computed before. So it is complicated, but not that cumbersome. Okay, so what is P1's total utility from playing C and from playing D? So when playing C, it should be the utility of the first guy when A1 is C. So let me annotate here what P1 plays. And then my belief is that second guy will be playing D. And then my second order belief is C. Oh, I'm sorry. Second guy is playing C. Then first we need to calculate the payoff, C and C, plus F2 bar, where B2 is C, C2 is C, times F1 A1 equals to C. Second guy plays C. Ah, forgot to add 1 here. Okay. Yeah, let me just check if this is consistent with the lecture note. Okay, it looks good. Okay, so C2, there's no C2 here. Should be C1. It's my second, it's the opponent's second order belief on my action. So it should be C1. Okay. Yeah, okay, yeah, now everything looks good. And then now what we need to do is to just compile all the information that we had. Let me just temporarily put this table here. Okay, so pi1 CC, so my payoff when we both play C and C is 20 plus F2 bar, what was that? F2 bar was 1/2. So if you're wondering where I'm looking at, here. So it was the answer for the first part of the question. So 1/2 times F1 was 1/2, 1 plus 1/2, which is 20 plus 1/2, 2/3, which is 20 plus 3/4. I'm really sorry today. So I forgot to put alpha here. Okay. Yes, I was thinking something is missing here. Yeah, so we want to compare. So this alpha means for the relative importance between fairness versus my consumption utility. So there's some term that we need to compare two different utilities. So I forgot to put that one. So we need some assumptions on alpha. So let me just put alpha here. So alpha and alpha. So this is the utility when I'm playing C. When playing D, U1, I'm playing D. My first order belief is that my opponent will play C. And at the same time, I think my opponent will think that I'm going to play C instead. Okay, so I'm deviating here. Then we need utility when I'm playing D and the opponent is playing C. We need F2 bar where B2 is C, C1 is C. You can see that this term is common. We have F2, F1. Now I'm playing D instead of C, and opponent is playing C plus 1, which is if we play DC, then we fall into this outcome, and my utility will be 25. F2 bar. I forgot to put alpha again. Same mistake. So if I was solving this the final exam, then I will get some points off. So forgot to put alpha. F2 bar is already computed above. It is 1/2. And then we have 1 plus, what was this? We already computed that above. It was 5/6. 5/6, which is 25 plus alpha 1/2 times 6, 11, which is 25 plus 11 alpha divided by 12. You see what is happening here? It's not mentioned in the class, but if it is a fairness equilibrium, then it should be a Nash equilibrium. And then, yes, let me conclude. Okay, so let me conclude, and then I'll show you what is interesting. So conclusion is that utility of playing D is larger than playing C. Okay. So U1, A1, D, D2, C, C1 is larger than U1, A1, C, B2, C, C1, C, which is saying that C is not a best response of player 1 to C of player 2. So when player 2 plays C, C for player 1 is not a best response. Okay. So this is different from the homework. In the homework, if I give you the hint, you will see that as the professor mentioned, yeah. So the strategy that is mentioned in the homework is a Nash equilibrium and also a fairness equilibrium, and it is a best response. Okay. In here, we have a small typo in the table. So in here, it was not a best response. Yeah. But in a slightly different problem that is uploaded on Canvas, it will be very similar to the homework. And then in that case, the Nash equilibrium and the fairness equilibrium will coincide. Okay. Yeah, so at the very first moment, when I was computing Nash equilibrium of this game, I was surprised because fairness equilibrium should be Nash equilibrium. So if there's only one Nash equilibrium, then then it should be pointing CC, but it was not. And this is because this version of the table is coming from the old version. But anyway, I think it was a good practice. You will see another question on Canvas. Yeah, I think this exercise is also useful. Okay. Yeah, so this is what I prepared for today. So I'm sorry if it was a bit unorganized. So if you have any questions, please let me know. Let me stop recording here.